Assalamualaikum and good day everyone. Today we will continue on the topic form of corrosion, and for today's topic we are going to talk about galvanic corrosion, which is one of the localized corrosion. So what is galvanic, or sometimes we call it true metal or bimetallic corrosion? Actually, for galvanic corrosion, it occurs when two different metals are electrically connected in the same electrolyte, such as like this. One metal and another metal which has different series in the EMF series, or one of them we call it less noble, one of them is more noble. Nobles mean it has a good resistance. Less noble mean an active material which is easily oxidized in the given atmosphere. So the more active, which is more energetic metals, will corrode faster. The less active metal will corrode slower and will be usually protected when they are connected together or side by side, placed side by side. So driving force for corrosion the driving force for corrosion is the difference in the electrode potential. So let's say you have these two connections between steel pipe and you have another copper pipe, okay, where you corrode, there will be corrosion at the interface between these two connected pipes. So basically, when we have steel and copper, steel are less noble or more active metals, so it will be oxidized. It will turn itself into anodic and it will change the oxidation state from 0 to +2. And then on the other hand, at the cathodic reaction, copper will be reduced to metallic copper. And then this is the overall question, combining between anodic and cathodic reaction. So let's say we have this example. Okay, we have two different metals. Let's say this one is painted, so it is protected. It will be inert because it has been covered by a coating. And then we have metal washer. This is the washer, okay, we call it washer. And then we have this screw. So the screw and the washer has different series in the EMF series. So therefore when they are connected, so when they are placed together, means they will be connected and forming one electrochemical cell because it has different potential, metal 1 and metal 2, and they are exposed to the electrolyte, which is the environment. So in this case, okay, if we have copper and steel, like this one, copper and steel, so steel will become anode, and once steel become anode, it will be oxidized. To avoid this, okay, this is let's say in this case this is steel, this is higher corrosion, more noble. Maybe we can well, even though the color is not steel, maybe stainless steel, okay, maybe stainless steel. So the steel will be corroded first, okay. Schematic galvanic coupling, we can see from here. If we have steel, okay, but we couple with zinc, which is more anodic, okay, more active. Zinc is more active, okay, so it will turn itself into anode, and this zinc will be oxidized. It will corrode and it will form zinc oxide. So steel will not corrode, and when they couple together, steel will become cathode. So this is how we protect the state structure. Okay, so this is what happened during the galvanic coupling. So this is a galvanic series. Okay, galvanic series in the seawater. Okay, similar to the EMF series, you will see the series from platinum to magnesium, where platinum is noble materials, okay, increasing inert toward upwards, and then followed by gold, graphite, titanium, until you reach magnesium, which is most active materials. Okay, however, in the galvanic series, if you look at this series, unlike EMF series, you can see in cornell, which is one type of nickel alloy, you will see stainless steel. Okay, if we have pure metal copper, we will see brass, which is copper zinc. Okay, so meaning that there are more than pure metals. Okay, the series will arrange according to different types of common alloy. Okay, and in fact, if you look at this nickel active, nickel passive, there are two conditions where at one point it will become active, and increasing the potential, it will become passive, and then break down the passive layer. Okay, that's the reason you will see nickel and nickel active and nickel passive. This is nickel passive, this is nickel active. Same goes to the stainless steel, which is active, and the passive stainless steel. So what's the difference between galvanic series and the EMF? Actually, the galvanic series will predict which metal will corrode. And then the galvanic series similar to the EMF, but it is for alloy in the real environment. Okay, so the comparison is, if you look at the EMF series, it's ordered by standard equilibrium potential and assume activity of solution species to be 1, and does not allow for protection corrosion product. But if we look at the galvanic series, it is the series is ordered by observation behavior in the service, so it allows for the corrosion product and can be defined for alloy. Okay, not only for pure metal. Okay, in the EMF series, it is only for pure metal. So different for every environment, and you have to set up the galvanic corrosion for the application of the environment. So the factors affecting the severity of galvanic corrosion are the size of exposed area of the anodic metal relative to that of the cathodic metal. Okay, if you have small cathode relative to anode, it will cause small increase in corrosion of anode. Okay, smaller cathode. Okay, so imagine you have two parts, one is small, one is big. Okay, one is small, one is big. Okay, if you have smaller cathode, this is small, so this is cathode. So then it will cause small increase in corrosion of anode. This is anode. So anode in larger size compared to the cathode. So smaller anode will suffer severe corrosion. Okay, if you have large plate and this is your anode. So anode is smaller compared to cathode. So this is a very bad situation because it will increase the corrosion rate. Okay, so the difference in potential between metals, which is anode and cathode, in the galvanic series. Okay, number one is the size. Number two is difference in potential. Okay, metal for anode and cathode much have very close difference, similar or close different in the galvanic series. So if you want to choose from the series, let's say there are 1, 2, 3, 4, 5, 6 metals or alloy in the series. Let's say this is your cathode. So now you want to choose anode materials. So anode materials somewhere below. Okay, so you need to choose. If you require to choose different materials, so you need to choose an anode which is just below the cathode materials. You cannot choose number 6. Okay, if 3 versus 4 is better compared to 3 versus 6, where this is the anode materials. Okay, so if your cathode material is 3 in the galvanic series, you are required to choose materials that number 4, okay, which is smaller gap, smaller differences in potential between the anode and the cathode in the galvanic series. Okay, the effect of anode polarization on anode, okay, also influence the severity of galvanic. Okay, some metal may passivate. Okay, so remember, if you are choosing for example aluminum, okay, as the anode, let's say in the series you in the series there are steel and aluminum is more active. Okay, if you want to select this steel as a cathode and then aluminum as anode, you have to remember aluminum has a tendency of polarization. Once it polarized, forming aluminum oxide, this one will be passivate. It will form a very good passivation layer. So it will turn itself into anodic, into cathodic when it coupled with steel. So this that's the reason you need to carefully choose your materials. Okay. So some experiments showing a test between the size and the type of material for investigate the galvanic effects, galvanic corrosion between the two materials. Okay, for example, in this case we have copper and steel rivet versus copper bar. So the large material is copper, the small material is steel. So in this case, steel are in the series, copper is a higher potential in the galvanic series compared to the steel. Okay, so steel will become anode. So if you look at this, okay, the small area is steel. This is anode. So this is anode. Anode is smaller size. After and then another case is a copper rivet. Okay, this is copper, and this is cathode. And the steel bar is anode. So anode is large. For case on the left side, anode is small. So after some time, when you expose to these solutions, 3% sodium chloride solution, after 6 months, you will see that the original shape of rivet seems like degraded. Okay, it dissolves in the atmosphere or electrolyte. But if your anode is more noble, you will see corrosion happen on the surface of the plate, but the rivet is still there. Okay, the rivet is still there. It still function as a rivet. It not dissolve and it's not corrode. Okay, and after 10 months, you will see that severe defects happen on the rivet. So remember, rivet will will join the two structure. So now it is destroyed, corroded, severe corrosion happen on the rivet. But on this side, you will see that the rivet is still there. Okay, corrosion happen on the steel bar instead of the small cathode. Okay. So in the galvanic corrosion, it also can occur between different phases in the same alloy. Okay, different phases. So this occur when one of the phases is much more active as a cathode. Example, okay, precipitate that contain copper in aluminum alloy may initiate pitting corrosion. So iron and copper impurities in commercial zinc may cause a large increase in corrosion rate compared to pure zinc. Okay, so why? Because they have another phases inside the alloy that giving an effect of different potential between the phases in the alloy. Okay, so this allow the galvanic corrosion to happen. Okay, so in crystalline metal, galvanic coupling can occur between grains and grain boundary also. Okay, the grain boundaries normally act as anode due to their atomic mismatch and possible segregation of impurity. Okay, so also this it's like a two different concentration of atom. Okay, for example, in this grain, in the grain, atoms are ordered, but at the grain boundary there are less atom. Okay, so the density is less, so it will give effect of galvanic corrosion. Okay, so in this case, there are two different phases, which is precipitate. Okay, precipitate and the parent alloy. Okay, phases, the majority of the phase is the alloy itself, and the precipitate will give, because of the two different phases inside the alloy, it will give an effect of galvanic corrosion. And in fact, galvanic corrosion also can occur in polycrystalline alloys such as the palladic steel due to the difference in microstructure phases. Okay, microcell will be formed. Microcell means a small scale of electrochemical cell will form between ferrite and cementite when exposed to an electrolyte, since each phase has different electrode potential and atomic structure. So let's say this is a lamellar structure. Okay, so the lamellar structure inside the pearlite. Okay, so let's say this is cementite, and this is ferrite alpha. So because there are two different phases, so they will have different electrode potential. Okay, and of course atomic structure also different. So they are contact at the interface. This is interface. They join together at the interface. So the whole interface will allow the galvanic corrosion to occur. Okay, so in this case, pearlite structure will be revealed with ferrite appears white and cementite appears dark. So this is cementite, it's appear dark, and the white region is ferrite alpha. So if you look at this microstructure, this is ferrite alpha. Okay, ferrite, and then the dark one is cementite. So how to prevent the galvanic corrosion? One, we select combination of metal as close together as possible in the galvanic series. Okay, so avoid the unfavorable area effect of small anode. Okay, no small anode and large cathode. Instead, you need to assign the small as cathode. Choose material that allow this small structure as a cathode and the large structure as anode. So this one, they still happen in the galvanic corrosion, but at a very slow rate. If you allow small as a anode, okay, if you allow this happen, so the corrosion rate due to the galvanic corrosion will occur very fast. So avoid this, avoid these effects. Okay, for example, choose the use of stainless steel screw on a large aluminum surface rather than a small aluminum screw on a stainless steel surface with a seawater environment, for example. Okay, if the similar materials must be joined, you have to insulate them electrically wherever predictable. Okay, apply coatings, okay, with caution. So add inhibitor is, if possible, to decrease the aggressiveness of the environment. For example, in this one, in the seawater environment, okay, you can control the environment by apply inhibitor in the environment. Okay, design for the use of readily replaceable anodic part or make them thicker for longer life. So it's okay. All right, let's say you have this structure, you know that it is small, it will corrode very fast, but this small part is something that you can allow this happen. For example, this small structure, you have to choose it as a anode instead of cathode. But the small structure that become anode must be something that easily to be replaced. Okay, if a permanent structure, it is very difficult to you have to avoid to make it turn into anode. Install a third metal which is anodic to both of metal in galvanic contact, which is catalytic protection. Okay, let's say you have this metal and then this metal and this metal. Okay, you between this metal and this metal. Okay, you have metal 1, metal 2. If you want to join this two metal which is different in the catalytic potential, electrode potential, so you will need to apply separator, okay, to avoid contact between metal 1 and metal 2. This metal 3 must be most anodic. Okay, most anodic compared to metal 1 and metal 2. Okay, this is good to protect both important structure. Okay, for example like this. Okay, for example you have aluminium. Okay, aluminium plate and aluminium bolt, and then you connect this aluminium with steel structure. So this between aluminium and the steel, all right, aluminium and the steel, you insulate them by using this insert. And in fact, these aluminiums and the steel, you insulate, okay, to avoid the contact between aluminium bolts and the steel. And another insulating washer, okay, to separate between aluminium bolts and the steel. Okay, I think that's all for this type of corrosion, which is galvanic corrosion. Thank you.